Okay, so thermodynamic processes, what we're going to do first is we're going to review. So notice there that it says, it lists the first law. Everything is based around the first law. Okay, so let's review what we know about the first law. There are 4 total things that can happen when it comes to the first law. Who can tell me one of those 4 things that can happen? The reason I included this picture here is to go over those 4 things, okay? To make sure we understand that those are the 4 things that can possibly happen, okay? Work is done to the system, which is positive. Work is done by the system, which is negative. He can go into the system or he can exit the system, okay? The heat going to the system is positive and the heat leaving the system is negative, all right? Now, as far as a first law equation goes, okay, there is, right now, what we have is this equation that needs to be memorized, all right? For some crazy reason, that's not on the equation sheet, all right? That tells us the internal energy. There are a couple equations, and these won't be the only ones, but there are a couple equations that also help us out with the work, okay? As far as the work is concerned, as far as this version of the work is concerned, that applies to these pictures down here. All right? If the initial volume is greater than the final volume, then that means work has been done to the system. Okay? If the initial volume is less than the final volume, then the work will come out negative. All right? And that will always be the case because that's why that negative sign is in that equation. All right? Another way we can calculate the work done is using the force times distance equation. All right? So, and related to this equation is this pressure equation there, the force over the area. So all those things you're going to need to apply in this stuff. All right? Okay. Also, as a review, you need to know the volumes of the cylinder and the volume of, essentially a box. And you need to have those. Those, I think, are in the, at least the cylinder one is on the yellow sheet, right? The equation sheet? Right. Okay. So here, let's get started with the first thermal process, okay? There are 4 total thermodynamic processes, okay? The first one that we'll go over is the isothermal process, all right? So, isothermal, iso means it stays the same. Thermal process, that means the gas is held at a constant, anyone know? Actually, it's held at a constant temperature. So write that down. You need to know this. Okay, very important. So the gas is held at a constant temperature. All right. Now there's 2 types of isothermal processes. There's the isothermal compression and there's the isothermal expansion. All right. The isothermal expression is when we've got a situation like this where we got a gas and we add heat to it. Okay. We add heat, but, I'm sorry, I meant add work. We do work to the system, but heat comes out of it. All right? Now, how is it possible? So this question here, and you need to know this, how can you go from this before situation where you got some internal energy, okay, to the after situation without a change in temperature? Because if there's no change in temperature, will delta U change? No. Okay, so yeah, go ahead.
Yeah, but the work that you do is able to.
Okay, good. So the only way you could do this is if you lose heat. Okay? The only way this can happen is if you lose heat. If you lose heat. Okay? All right. Now, you need to know how all of these things apply to the first law. So here's the first law. Since delta U, okay, so you should have this memorized. Delta U is equal to what? Okay, 3/2 nR delta T. nR delta T. Okay, and because the change in temperature, what's the change in temperature going to be if it's held at a constant temperature? Okay, it's going to be 0. Okay? Then that means delta U has got to equal what then? Okay, delta U has got to equal 0. All right, if delta T equals 0 and delta U depends on delta T, then delta U has got to be 0. So what does that imply to our first law? What does that do to our first law of thermodynamics? Okay, delta U becomes what? No, it doesn't break it. Delta U becomes, this part becomes 0. Good. This version goes like this. It becomes negative delta W. Negative delta W is equal to positive delta W is equal to a negative delta Q. What's that?
Can it be the other way too?
It will be for the other situation. Okay? But for the isothermal compression, it's got to be this equation. Okay? Because what it's saying is this. The heat that we're adding, just look at the picture. The heat that we're adding
is equal to the net, yeah.
Is equal to the work that we're adding. I keep saying that. The work that we're doing to the system is equal to the heat lost. Okay? All right. Now, you need to know what that looks like on this pressure volume graph. They're always written as PV, but I wanted to write the whole thing out so you knew what it means. When something is undergoing isothermal compression, it's going to have a curve that looks like this. Okay, an inverse curve, and this is called an isotherm. Okay, why do you think that curve is called an isotherm? Because everywhere along that curve, what is happening? It's got the same temperature. Okay? All right, so that's an example of isothermal compression. Now, what this means, so let's make a statement. This says that the work done to the system, is equal to what? Okay, is equal to heat lost. Okay? All right. Then we're gonna go into isothermal expansion. That's the next version of the isothermal process. Okay? So in this process, we're going to add heat to the system. Okay? And that system is going to do work. How can I go from that situation where the internal energy remains the same before and after? How is that possible without a change in temperature?
If the heat added equals the work done by the system.
That's right. We've got to, only way that's going to happen is if we gain heat. Okay? And so my equation that I'm going to put in this box that's similar to this equation here is going to be what? What version of this equation? Yeah, it's the opposite. It's going to be negative delta W is going to equal the positive delta Q. Okay? Oops. Let me make sure I get the right one there. Positive delta Q. Now, what do you think that looks like? What do you think an isothermal expansion looks like on the pressure volume graph? Well, yeah, it's kind of like the opposite of that. It's just we're going to go in this direction. Okay, it's still an inverse curve there. All right. Now, again, this equation here comes from the fact that delta U has got to equal 0. Okay. All right. So one of the things you need to know is how to go from this equation, from the first law equation, to that equation, and to that equation. Okay? All right. In this case, here we said work done to the system is equal to the heat lost. What's happening in the isothermal expansion? Good. So actually the heat gained, right? Oh yeah, okay. But we got to add the heat first, right? So let's say that the heat added to the system. Okay. So heat added
Why does it matter?
to system, because generally speaking, you add the heat and then see how much work gets done. Okay. System becomes work done by the system. Work done by the system. Okay, now for the isothermal situation, okay, remember we've got this equation that I told you guys to be able to use. We've got the P1, remember this one, P1 V1 over N1 T1, okay, and that will equal P2 V2 over N2 T2. Okay, in the isothermal situation, what can I get rid of in this equation? Okay, I can get rid of the temperatures. Okay, and if we assume that the number of moles are going to remain the same, what else? The ends. So in an isothermal situation, when you're solving these problems, your gas law equation is going to just be this part of it. Okay? All right. Now, the key ideal gas law equation for isothermal situations is basically these two. Okay? So, for this, I'm kind of running out of space, so I'm going to write it up here. The first law equations, what you need to know is essentially what we just said. The positive delta W is going to equal the negative delta Q. So you have to be able, you have to read the question and find out what's going on and apply the right situation to it. Then that's a positive delta Q. Okay? So that's the isothermal situation. Okay. So let's check out, the next one is the adiabatic process. Okay? An adiabatic process means that there is no heat that flows into or out of the system. Yeah, I'm sorry for how those were stapled. Okay? In an adiabatic compression, if there's no heat, what does that tell us about delta Q, the change in heat?
It is 0.
Okay, so that's going to equal 0. All right? If I plug that into this equation, what do I end up with?
Delta U equals delta W.
Good. I end up with this. I end up with delta U is equal to delta W. Okay? So, in this example here, if this is completely insulated and I can't gain or lose heat, whenever I do work to the system, what is that going to do to the internal energy? It's always going to increase it, right? Any work that I do has got to increase internal energy. So, what will that do to the volume? The volume is going to decrease. What about the pressure? That's going to increase. And what about the temperature? That will also increase. Okay? So this is what this looks like on the pressure volume graph or the PV graph. Okay, you're going to have to look at a lot of PV graphs. So what I'm drawing here, these are two different isotherms. Okay, and what in an adiabatic compression, what happens is you go from the lower isotherm up to the higher isotherm. Okay, so that's, what's that? They don't have to be. Okay, and just so that you know, this is the higher temperature isotherm. The further away you get from the origin, that's the higher temperature isotherm. Okay, so let's write down our statement for this. So this means that the work done to the system, is going to be equal to what? Equals the what?
Change in internal energy.
Okay, equals the, let's say the increase equals the increase in internal energy. Okay? Because we can't gain or lose heat in this case. The increase in internal energy. All right? So this is a pretty easy one. All right. So the other situation that we can have is the adiabatic expansion. All right. So that's where the situation does work, or I'm sorry, the system does the work. Okay. And the internal energy decreases. So the equation for that is just going to be the exact opposite of the one we had before. That's going to be the negative delta U is going to equal a negative delta W. Okay? In this case, what happens to the pressure? I'm sorry, what happens to the volume? It increases. What about the pressure? Decreases. And the temperature? Decreases. All right? And so the way this looks like on here is it goes from the higher temperature isotherm to the lower temperature isotherm, like that. Okay, on the pressure volume graph. All right, and so this means work done by the system. Okay, work done by the system is going to equal what? Work done by the system is going to equal the decrease in what? Good, the decrease in internal energy. All right? So that, that obviously makes sense. The work done by system equals, I should put equals there, right? Equals the decrease in internal energy. All right, so I got a little example here. It says 0.25 moles of gas are kept at 1150 Kelvin. The gas undergoes adiabatic expansion reaching 400 Kelvin. How much work was done on or by the gas? Okay, so in this case, is that adiabatic expansion or adiabatic compression? Okay, expansion. So I always go to my first law in these problems, okay, because they emphasize the first law. Which of these two am I going to use? I'm going to use the top, or am I going to use the bottom one? Okay, I'm going to use the bottom one. So I want to know how much work is done by the gas. So I know that the work done by the gas has got to be equal to what? The change in internal energy. So if that's true, so I don't have an equation here that I can use. So if delta W is equal to delta U, what equation am I going to have to go to figure out the change in internal energy? Good job. We have to go to this one. 3/2 NR delta T. Okay? So that becomes 3/2 times 0.25 times our gas constant, which is 8.31. Okay, and remember we always go final temperature minus initial. So we'll go 400. That doesn't look like a 400. 400 minus 1150 Kelvin. Okay, and I think I have that value for you. Actually, I don't. You'll have to just... Negative 2,337. Okay, joules. Okay? All right. So let's look at what other equations help us in adiabatic process problems. So remember, these are the P1 V1 over N1 T1 equations. Okay, N1 T1 is equal to P2 V2 over N2 T2. So in this case, what happens? Do I get any breaks on this one? Is anything left constant? N is left constant, right? Other than that, I really get no breaks. All right? Okay, key first law equation. Okay, the first law equation is just the two that we mentioned, delta U is equal to delta W. Okay? And right here, I'm going to take a quick little break here and stop. Topic is the isobaric process. Okay? If you guys watch the weather, they show those isobars. Everywhere you see an isobar on a weather map means it's got the same or constant pressure. Okay? So that's what it looks like for isobaric compression. All right? Now, if you see a problem and it says it's an isobaric situation, then you get a little down because there's no brakes on the first law. Okay? The first law stays. The delta U, delta Q, delta W, they all stay the same. Nothing becomes zero. All right? So no brakes for the an isobaric situation. All right? Now, in the isobaric situation, what's happening is this. In order to maintain a constant pressure, work has to be done by the system, and this is a lot of times where you see they put a mass on top of the piston because you'll have a constant you'll have that'll make a constant pressure, okay? And then you lose heat. Okay? One of the things you need to know is the work that you're doing does not equal the amount of heat that you're going to lose. All right? So these are an isobaric situation means you got to use the full first law equation. All right? Now, with a first law equation, we've seen different things that we can plug in for delta U. You need to have this equation memorized, okay? But because PV equals nRT, I can replace the nRT with PV in this equation. So you need to know how to come up with that equation as well. All right? Now, we can prove that delta Q is equal to 5/2 nR delta T as well. So you need to know this equation, and you need to know this equation. You can prove it by using the first law, and I'll show you that sometime if you want to see it. Okay?
But those aren't going to be on the equation.
No, not yet. Okay?
Not yet.
All right. Delta W, it won't ever be. But you still, it's really important that you can be able to derive it.
It's just going to scare you in the back.
Delta W, but I probably, be honest with you, I probably should put it on there for next year. Delta W that equation is on the sheet, and because PV equals nRT, right, that PV I can replace with N delta T.
Would you put all those on there then?
It might be, yeah.
Sucks for next year.
All right. Well, the thing is, you have to be able to derive them anyway to solve these problems, right? Okay. And one of the things you need to know is that, yes. Okay. For right now, just use the sheet. All right. Basically, what you do is just to show you real quickly how you would do it, is you would plug PV into there, right? You would plug 3/2 PV into there, and then that would make this have to equal 5/2 PV. Okay. All right. This area here, so in an isobaric situation, the pressure volume graph is just always horizontal. This area is called the work. And on your web assignment today, you're going to need to calculate that. So the area underneath the pressure under the pressure volume graph, okay, is always equal to the work. Okay? All right. In this situation, you should know that the temperature actually goes down, okay, in the isobaric situation. All right? Okay, so no breaks there. Okay, so the other situation that we can have, the other isobaric situation is the isobaric expansion. And in this case, the pressure volume graph looks like this. It just goes horizontal like that. The area is still the work, okay? This area here is still the work, so that doesn't change. This is still equal to the work. All right. Now, and again, the equation that you still have to use, it's still delta U is equal to delta Q plus delta W. Okay. In my gas law equation, in P1V1 over N1T1 is equal to P2V2 over N2T2. What do I get to cancel? I get to cancel out the P's
And the N.
and the N's. Okay, so that's what that equation would look like. All right. In the first law, do I get any breaks?
No.
No breaks. So you have to use a whole first law equation. Okay. So again, the isobaric situation, you have to use a whole first law equation. Make sure you know all of those equations right there. All right. Okay, the final process is an isocoric process. Sometimes you'll see the word called isovolumetric. Okay. Since I said it's isovolumetric, that means the gases are kept at a constant what? Yes, kept at a constant volume. I almost wrote down constant. At a constant volume. Okay? So isocoric means that delta V is going to equal what?
0.
Is going to equal 0. And since delta W is equal to negative P delta V, that means what then?
0.
What 0?
Delta.
Good. That means the amount of the change in the work, so no work's being done. So does that give us a break in the first law?
Yes.
Yeah, it sure does. It means that we can say that delta Q or delta U is equal to delta Q. Okay? So all the heat that I'm adding into my gas, notice the volume is not changing. All the heat that I'm adding to my gas goes into what? Yeah, it just goes into the internal energy. So what we can say here is that heat added to system, heat added to system,
So for like these problems, will they say like in the problem the gas is kept at a constant?
yes.
We'll know that it's
Yeah, somehow they'll tell you enough. Yeah. Yeah. Equals the increase in internal energy. All right? Internal energy. Now, the other version of this is where we've got decreasing pressure in an isocoric process. So my equation there will be this. Negative delta U, okay, because is equal to negative Q. All right? So in this situation, again, we're keeping the volume constant. We're losing heat. So what does that do to the internal energy? Yeah, internal energy is going to decrease. All right? So that's going to go down like that. Okay? So in both these situations, it's really important to notice, okay, that heat must be added. In an isocoric situation, heat has to be added. Okay? This is like one of those questions on the AP test that you'll see and go, wait a minute.
It has to be low.
Yeah, heat must be lost. Okay? So in the decreasing pressure version of this means that the heat lost equals what? Yes, or we don't lose internal energy, we decrease internal energy. I guess we could lose internal energy. I guess you could say that. Internal energy. Yes.
In real life, would this be applied to like car engineering and airplane engineering?
Yeah, but you lose, in those situations, you lose way too much heat. But yes, you do. Okay. All right. The key ideal gas law equation for isocoric. All right, so we got the P1V1 over N1T1. Okay, that equals P2V2 over N2T2. What do I get to cancel from that?
V and N.
Okay, I get to cancel out the V's and the N's. All right, and the key first law equation for isocoric process are these ones, right? Delta U is equal to delta Q.
I like.
All right. Okay, so you have to understand in these problems what they are.